All over the world at the moment, of course, climate and weather change is a vital topic. Everyone's concerned about it, but there's some peculiar factors that are affecting the whole of the understanding of this. So today, if I can, I'd like to give the bigger picture view, which brings in all the factors that we already know about, but also some additional factors which are very vital to understanding the real issues at stake. Now, my background is first of all, I had a company that consulted worldwide for infrared heating, drying and evaporation. I also taught fluid mechanics and heat transfer for 40 years at the university, as well as did research in fluid mechanics and heat transfer and applications and novel applications in industry. So I'm interested from not only the chemistry, not only the physics, but the engineering, the macro mixing and what's happening in the atmosphere. So today, if I can, I would like to open the door and to interest you. I've put a couple of motivation slides just to catch your attention. Well, first of all, as we all know, or all been told, carbon dioxide went up 100 parts per million in 100 years. So fair enough, of that order. And of course, the temperature went up 1 degree in 100 years, 14 to 15 overall average. And so at the same time, everything would have heated up. The whole world would have heated up, if that's true. And so water vapour would have gone up actually 280 parts per million in 100 years, and that means it's about 2.8 times greater than the carbon dioxide increase in 100 years. And of course, water vapour, as we'll see shortly, is by far the stronger greenhouse gas, and we'll look at that shortly with the evidence for that. So this is part of the natural water cycle. Very big in this world, very big indeed, and we need to talk about that. The second one is called the natural carbon cycle normally, but I would call it the natural carbon dioxide cycle, because carbon dioxide not only reacts, but also biologically is transferred into all sorts of stuff in trees and orange juice and apples and all sorts of growth in crops and so on. So if we just take, is this a second motivator slide? This is a plot of carbon dioxide versus time. It's a one-day cycle, and it's taken around corn and soybean, and you can see this is at night time, and to the left and right of those two figures, but daytime you can see the level of carbon dioxide drops. So at night time it's around about 400 parts per million, and at night time it drops dramatically to about 300 parts per million. Now, we just said a moment ago that carbon dioxide has allegedly gone up 100 parts per million in 100 years. But the atmospheric carbon dioxide drops 100 parts per million in 3 hours. So here we've got a phenomenon that we must examine as well. And so it's the local lowering of carbon dioxide near crops. And of course it'll occur near trees and so on, but not at the same rate perhaps, but in all crops. And to be honest about carbon dioxide, this is a plot of carbon dioxide versus year for a longer period. And you can see people say that carbon dioxide is going up around about 2 parts per million a year. Well, that's true, but it's not all the truth, because carbon dioxide goes up 10 parts per million in 6 months and goes down 8 parts per million in the next 6 months. As you can see, the data's there, and it's as you can see down the bottom there, it's US NOAA data, which is on the web, and in net effect, of course, it's going upwards by 2 parts per million. But there's a bigger picture here. In this presentation, I'm only going to take 2 references on a website which you can easily get yourself. They're accepted, they're not, they're widely used. The first is a radiation spectrum, and the second is a humidity chart or humidity calculator. That's all you need in this presentation, and I'm only use those with perhaps a couple of references to something else only. Now, if we start back from the sun, we know all energy comes from the sun, and it goes through outer space, it comes to the atmosphere, and it hurtles towards our planet. And of course, our planet is mainly solid Earth and liquid oceans, mainly. Now, in outer space, it does nothing. Radiant energy does nothing in outer space, and we'll talk about that. And in the atmosphere, 99% of the atmosphere that we live in is nitrogen, oxygen and argon, and it does virtually nothing in that. Now they get involved, but not directly with radiant energy. So we've got two issues to consider briefly: space, outer space, and local atmosphere. So look again now at solar radiant energy running unimpeded or being transmitted unimpeded through space, and we come down to through 150 million kilometres through absolute zero. It's minus 273, the coldest temperature we can have, and a vacuum, zero pressure. And so it does no heating, it does no excitation of anything because there's nothing there, and so radiation does nothing, absolutely nothing, coming through the atmosphere. And that's our first point. And that's pretty important to realise, that radiation requires something to heat up. It can't heat up in a vacuum, and the principle of the thermos flask is why we use that anyway. The second point is that when we come to our atmosphere, called the troposphere, it's naught to about 15 kilometres. That's the bundle of air we live in, and of course it's about 80% of all the air is in that zone. And then, so what we've got here is almost 99%, as we said, nitrogen, oxygen, argon, and radiation does absolutely nothing directly. It does something indirectly. We'll talk about that a little later. And so that covers our second point. So now we're free to say, well, let's put us all on the same page and ask, what is radiation and what does it do? So first of all, it's called electromagnetic radiation. And in our system, in the world system, we have visible light, infrared energy, radiation, ultraviolet. Now, of course, there's other types. There's radio waves, or you could say that's electromagnetic radiation, and so on. But we won't be dealing with those. Now, only 56% of radiation ever gets to our planet Earth. 44% of that 56% is visible, 48, about half, is infrared, and a small amount is ultraviolet. Now, visible, you well know, we've taught at school the white light, and we get the colours, red, orange, yellow, green, blue, indigo, violet, and you can see from the rainbow. And so we get the refraction and reflection of visible light to give colours. Now, the infrared energy is the stuff that makes us feel warm, and so we feel infrared energy in our body, and so our nerve endings are little eyes that pick up infrared energy. Our eyes up here pick up the visible energy, and of course vitally important. Now, visible normally is not used much, we might think, but it's certainly vital in photosynthesis, where carbon dioxide is converted to oxygen, and the carbon out of the CO2 atom converts to carbohydrates, and all the molecules, orange juice, orange skin, apple juice, flowers, petals, cellulose, the lot, comes from the atmosphere. The atmosphere is the feedstock for everything. A little bit comes from the ground, but not much. Now, if we go to infrared, as we said, it makes us feel warm. So it heats the solid earth, it heats the liquid sea, and it heats up some atmospheric gases, which are called greenhouse gases, and we'll talk a lot about that today. So if we take the ultraviolet one causes sunburn. It causes, not that you don't feel it, but it does cause the skin to go red, or it causes skin cancers, or as you get older you get all these black spots all over you, and so it causes those. And of course that's why we use sunglasses, because of the reducing of the rate of ultraviolet. Now, this is a pretty important point. Radiation coming from the sun interacts, and the question is, what primarily or foremost or number one interaction? What is number one? Now, it's pushed that greenhouse gases are number one. I just want to highlight why it's not necessarily true. We have non-condensable greenhouse gases. One greenhouse gas is called non-condensable, it's water vapor. But actually, what the energy from the sun hits liquid water first. Clouds, 2/3 of the world is clouds, liquid water droplets. More than 2/3 of the world is ocean, so there's a lot of liquid water. And so those two together make up the two important things in this question. What is major? And of course, in between, we have water vapor, which is a gas. Now, there's something which people don't talk about today. We have liquid droplets in the air, very small, can't see them, but they haven't agglomerated to form a cloud yet. So we have that as well. And most of the research data excludes all of that. So water droplets in air and so on. And I want to highlight some of this today. So I would say this, from an engineering practical point, is very major. Coming back to our electromagnetic radiation issues, we've got water droplets are important, and of course if we just expand our thinking, clouds, mists and rain, we've got specific atmospheric gases like carbon dioxide and water vapor and others we'll talk about. And then we've got water vapor, the gas, we've got oceans and lakes in addition to the seas and oceans, additions and rivers of course, and we've got the solids on Earth. Now the solids on Earth, when the air molecules hit it, they are carried away with extra heat. So we've got what we call convection heating, very important. Now electromagnetic radiation is important, but there's still more, and I want to revisit it shortly, but I want to go on with something to give, to add to these details of radiation. There are two vital issues I want to highlight at this time. One, it concerns the natural water cycle. It's very big in this world. And the second is the mixing or the turbulence in both the atmosphere and in the oceans, which are often not counted of high importance, but they are, and I want to show why. So let's examine the natural water cycle. Now the natural water cycle is pretty obvious. We have evaporation, liquid water to water vapor, gas, and they then condense, if you like, or form clouds or microdroplets. The microdroplets agglomerate, and when the droplets get big enough, after aggregating together, they precipitate as rain and go back to Earth. And so there are large energy changes, and they're not solar energy changes, and they're not radiation energy changes. There are a lot of energy changes that are neither they're not radiation changes. So here we've got water returning to the land and sea, and so as the rain falls, it cools the air, then cools the land and sea. An easy proof of that, when you're driving a car, look at on a sunny day and it starts to rain, you'll see the temperature drop 3 or 4 degrees when it rains. So the extensive mixing in this water cycle, which is natural and occurs all the time, all around the world, everywhere, and to a different degree. So it is unique to the natural water cycle, and we must consider it, and we do get massive mixing and massive energy changes, which are not radiation changes, or could include them, but they're not mainly those. Now we come to the very important point here. The more the Earth heats up for any reason we like in our brains to think about any reason, the more water will evaporate. The more water evaporate, the more clouds will form. The more clouds will form, it'll form like on a hot day, a cloud forms an umbrella, and then it rains, it precipitates, and then cools the air, cools the ground, and so on. So we've got this terrific, massive compensation, natural compensation. So if it heats up for any reason, it'll compensate, it'll regulate, it'll correct and buffer. And this is a vital issue in the natural cycle. Okay, so the second issue, major issue I'd like to highlight is mixing in the atmosphere and also in the oceans. So we have massive mixing. Now we all are well aware of this. But in the atmosphere, we have breezes. We know those. We've seen people in hang gliders going up on thermals. We've got winds, clouds, storms, and gales. And we've got hurricanes, cyclones, and typhoons. So there's massive mixing, tornadoes as well. And some of those are very intense. Some are small. Some last for a long time. Some affect a whole country or a zone of a country. Very important. And then we have jet streams. We'll talk about more of that, how important they are. And trade winds in the southern hemisphere, and the roaring 40s, which we have down south in the southern hemisphere. We talk about those. Now in the ocean, we also have massive mixing. We have ocean currents, we have conveyor belts. They move, continuously moving large quantities of warmish water at the surface from one country to across the whole, say the Atlantic, or right up into near Sweden and past France and England. And then we have tides in and out every day, waves, the local surface things which occur with mixing. Again, this is all to do with mixing. And we have undersea mixing caused by fissures and cracks, caused by bubbling up carbon dioxide or bubbling up liquid methane or liquid carbon dioxide. And of course, we have the two connecting things, which we call the La Nina and the El Nino. Now, they are movements of warm surface water across from, say, Peru towards the Asian continent, and in the warm water evaporates, and there's a shift of that over a period of time, and there's a shift back. And so it's cyclical, it's over a cycle, and it's very important. They're the connecting links, but there are more connecting links than I've just highlighted there. Now, most mixing actions do not require solar energy at all. Solar energy is where we get all our energy, of course, but what's happening? Because they occur and operate at night in the dark. So it's not solar energy driven. And in fact, I've got a short article which I show that 28 mechanisms that are non-radiation mechanisms, which could be highlighted. Now, as I said, we're going to return to radiation and greenhouse gases, because this is the most talked about issue today. Now, technically, you only need one reference, and it's available on the web, and it's called Atmospheric Transmissions. It's in Wikimedia, not Wikipedia, Wikimedia, and this is what it looks like. That's the picture you get, and I want to explain that today because all the data and the discussions I'm going to go on with on radiation require this particular plot, and you can get access to it. You don't need me to interpret, I just need to highlight a few points to open the door of this whole thing. So all radiation is covered in this plot. Now, it looks like this. So when you go on, you'll find solar radiation and then re-radiation from Earth, and I just want to highlight a couple of factors. Take water vapor. There it is, and you can see it has two zones where it absorbs energy. Now, I should highlight, none of these greenhouse gases absorb and retain. They immediately, within a microsecond, re-emit. And of course, it does change the kinetic energy, the movement of the particles, and it changes the whatever nature of vibration of it, the rotation of it, and collision with them. So what we've got is, say, carbon dioxide. You'll see that it's only got two smaller bands than water, two small bands, so it operates only over two narrow zones. Look at methane. Not only doesn't absorb much, it's not high, but it again has two different small areas. So as I said, it's in Wikimedia, it's under Atmospheric Transmissions. Now with greenhouse gases, there are four key factors. If we miss these or highlight one, we distort the truth. And I want to do this today, examine what are they. Quantity is one thing. Secondly is effectiveness. Thirdly is the competition between these greenhouse gases. And then fourthly is uniqueness. What makes a certain greenhouse gas unique? So let's look at quantity first of all, relative quantities. Now, we can talk in terms of quantity as concentration, that is the mass per unit volume or mass per unit mass of air. If we take water vapour, carbon dioxide and methane, water vapour in New Zealand is 1%. In the tropics it gets up to 4%. Carbon dioxide is 0.041% about, and methane is 0.0019%. Now if you look at this, water vapour is 25 times higher in concentration than carbon dioxide. As you can see, it's that important, but only 5% is man-made. So water vapour is 450 times more concentrated than water vapour is 450 times stronger than carbon dioxide in terms of quantity. Now if we take methane, it's 5,300 times greater. 5,300 times greater than methane and several hundred times greater than carbon dioxide. So quantity is the key issue to start with. That's only beginning. But I want to illustrate this because most non-scientific people might have trouble just wrapping their brain around it. So let's look at Auckland. Auckland has a population of 1.7 million, and let's assume that 1.7 million represents all the atmosphere, 100%. Now water vapour, which is number one greenhouse gas, and we'll prove that later, it's 1%, it would be 17,000 people. Carbon dioxide, number two greenhouse gas, 0.04%, it's equal to 700 people. And methane, number three greenhouse gas, is 0.0019%, which is equal to 3 people. The question, of course, is how can just 3 in 1.7 million cause a lot of trouble? And there's a big shift, a movement and discussions about the effectiveness of methane, but there's not much of it and it can't do much anyway. And I think we've got to be honest about that. So on relative quantities, clearly water vapour is number one. Now if we combine the second and third points of radiation, and I'll combine effectiveness and competition together. Let's have a closer look at radiation spectra again. And this is a teaching slide, so I'm going to develop the what we've shown that little diagram before. So this is a teaching slide. It's an explanation of what's happening. The red thing is the sun, and that's solar energy. There's the particular graph, which is freely on the web. It's not my data, it's on the web, it's been around for years. It's all incoming solar energies on the left-hand side, and it's solar energy. Now if we come to our graph, on the right-hand side is 0 to 100% amount of radiation absorbed by all greenhouse gases, and remember I said it is instantly re-radiated. Now radiation is called a short wave radiation. Let me explain that. Mathematically, we can talk about radiation as a cyclical up and down thing, and between the maximum peaks is called a wavelength. So we measure wavelength. So if it's a short wavelength, it's got more punch. If it's long wavelength, like TV, radio waves, big wavelengths, it's got not much power, but it still needs a big amplifier to amplify it and develop it. So let's look at that. Radiation from the sun is in the 0.2 to 3 micrometers. Now what does that mean? A micrometer is a millionth of a meter. So between 0.2 and 3 micrometers. Now let's look at visible light. Now from school you had red, orange, yellow, green, blue, indigo and violet. And that's where it sits in that region between 0.2 and 1, just below 0.7 and down. And so we know that, and that's obvious. Now look at the left-hand side, you'll see that's one there is violet, and so to a slightly smaller wavelength we get ultraviolet, and it's named after violet going to ultraviolet, and that's that spectrum. It's an important spectrum, it's the one that's causing damage to our bodies and organic materials. Now if you take to the right you've got red, and that's to the right of that, longer wavelengths, 1 to 3 for example, 0.7 to 3, it's the solar energy spectrum. So basically the bottom graph is really, the bottom along our graph is solar energy band, IR, infrared, UV and visible. Now we can go on with the actual, we take that same diagram again, this is solar energy coming from the sun, and now we're going to really discover what's happening. There's where the visible light would fit in there, just show that again to remind us this is the amount absorbed and re-radiated. Now let's look at carbon dioxide. Now doesn't that look good? There's one 100% band and one about 70% band, and they operate only at about 2 bands of energy coming from the sun. Pretty good, eh? Then we move on to methane. Now methane has got, not in the same spot, but it's in between, but it's very small. If we go to nitrous oxide, look at nitrous oxide to the right. It's very small, it's very narrow. Now we come to water vapour. What does water vapour do with solar energy coming in? Now look at that. It immediately covers pretty well all of nitrous oxide, most of methane and most of carbon dioxide. Just go back and show that, and you can see how competition comes in and how water vapour, which is far higher concentration, 24, 25 times higher in concentration than carbon dioxide, dominates. And so it's pretty fair that water vapour dominates incoming solar radiation. Now once we're cleared on incoming solar radiation, let's look at re-radiation it is, back from Earth. It's travelling all the time, by the way, night and day. So this is the right half of the plot. That's the blue part there. And again, we have a different wavelength range, 3, 5, 7 to 70 micrometers, 70 millionths of a metre. That's what 70 millionths of a metre. And of course, we've got the 0 to 100%. Okay, so now we can analyse re-radiation back from Earth. Carbon dioxide now has 200% bands. Looks good, they're wider, it looks healthy, looks like carbon dioxide's a bigger number now. Look at methane. Yes, it's gone up too. Two big peaks, not 100%, less of course, but two big peaks. Let's look at nitrous oxide. Nitrous oxide's got these 4 peaks. One's very small, one is totally covered by carbon dioxide, so carbon dioxide would win on that battle, and the other ones are kind of in competition, as you can see. Now let's look at water vapour. Now water vapour, this is water vapour in the air, and of course keep in mind none of these research so far have covered water droplets, and that's what will make it even worse, but we won't go down that track today because it's unused, but it's vital, it's there. Now there's water vapour. I'll just show you again. Water vapour dominates everything except a couple of spots with the grey nitrous oxide and methane, but nitrous oxide, it's not much of it. It's got to compete with methane, and it's much bigger, and so we got water much bigger again. So here we've got again water vapour totally dominating the outgoing radiation. So we could summarise this. If we look at the compensate for the overlapping curves and everything like that, we could say that water vapour is 35 times more radiation effective than carbon dioxide, 35 times. And it's on methane, it's 5,900 times more radiation effective. Now this is governs or was used from all the data we've shown today using a complete analysis. But it's interesting that man-made is only 5%. So water vapour is now 700 times more radiation effective than man-made carbon dioxide. So we've got to be careful here that we don't distort the whole picture. Man-made carbon dioxide from all sources, from cars, vehicles and generation of power systems, it's water vapour is 700 times more radiation effective, and that's what really matters. So we've covered quantity, we've covered radiation effectiveness, and we've covered competition. Now we're going to come to uniqueness. Now this is the water vapour is the only gas that changes phase. What do we mean? It goes from gas to water to ice, and of course ice can sublimate and go straight to gas without going through you can put your clothing out in a freezing weather and the clothes will remain dry and it won't ever get wet because it goes straight from icy clothes straight to water vapour gas. It's the only gas that condenses. No other gas in the atmosphere does this. So we have cloud droplets, rain, mists and fogs and sleet. Very important, over and above all that we've talked about so far. Rain, mists, fogs and sleet, and they interrupt, affect solar energy. So we've got to be very careful that because we've got, if you want to know, 423 trillion tonnes precipitate each year. 423 million tonnes of water rain down on this earth every year. So it's pretty important. It's the only other gas that freezes. No other gas freezes in our normal atmospheric system. It forms ice crystals, it forms snow, hail, and of course, naturally, these two things together, I'll just take that back, these two things together, freezing, condensation, and change of phase makes water unique, and that's the uniqueness factor of it. Now, the energy changes are not necessarily radiation. Most of them are not. Latent heat changes, all sorts of other changes. We've got concentration changes, droplet size changes, crystal size, ice and snow particle changes. But we now change the whole topic. We've got to move to population, not concentration changes. And this is rarely, if ever, mentioned today. Population is the number of particles per unit volume or zone. Hence, we must bring in all factors. It's not just the natural water cycle either. It's not It's massive atmospheric mixing. It's extensive ocean mixing. We've got to consider all gases, liquids and solids. We can't just leave them out. Radiation to ocean liquid and radiation to the earth is also vital, and radiation to greenhouse gases. But it's important to highlight it's not just radiation and greenhouse gases. Okay, well, radiation is very important, but there's far more, and I want to highlight this. First of all, let's just take 3 illustrations. The first one is pictorial, you'll see it, and it's very powerful. This is a rapid fog formation. It occurred within 15 minutes, and it came and went out to sea within 15 minutes. It's from our place. I was having lunch, and it wasn't round near freezing point. It was 23 degrees in the air around lunchtime. I took my cell phone out and just belted away at those within 15 minutes. And you can see how fog can form. They're liquid droplets, as you can see. So they're not big enough to fall as rain, but they form now as liquid droplets, and you can't see through them, as you can see there. So water vapour becomes highly important, and water vapour, if you really want it, there's the second reference. The only thing I'm really referring to is a graph, but this is the easiest way you can do it. Now, no one can deny this because it's all calculatable. Normally it's a graph, but go to LenTech, L-E-N-N, Tech, and you can put in your own and get your own data. This is what it looks like, and here's a typical humidity plot, and this has got 18 down to 18 degrees and a certain value of humidity. You type in relative humidity, and you can get the actual mass, grams of water per kilogram of air, dry air. And the relative humidity is there. If you change the relative humidity, just put the number in and it gets the answer. Now, that's the first one, visual. Now, the second one is calculations. Now, this is quite astounding. A half a degree rise, which happens every day, far more, can produce more water vapour than the total increase in carbon dioxide in 100 years. A half a degree, and it goes up 5, 10, 15 degrees each day. Walk out from under a shady tree, it goes up 10 to 15 degrees. If there's water around, the amount of water vapour increases. Now, this is taken from the LenTech calculator. 10 to 10.5, keep the humidity, relative humidity constant, goes up 118 parts per million increase. That's more than the 100 parts per million carbon dioxide in 100 years. If we go 18 to 18.5, it's almost 2 times the carbon dioxide in 100 years. And if we go 20 to 25 to 25.5, that's over or almost 3 times the carbon dioxide increase in 100 years. So it's important to see temperature alone, keeping a relative humidity constant, temperature increase, a small amount alone, can make a massive difference to the amount of water vapour, and we've already shown water vapour is 25 times higher than methane, carbon dioxide, and also far better in its ability to work with radiation. Again, so water dominates over carbon dioxide in temperature change. Now, this one is most astounding, and I've not seen this anywhere throughout the world so far. Now, this is for no temperature change at all. This is keeping the temperature constant, a 2% increase in relative humidity with no temperature rise can produce more water vapour than a 100-year increase in carbon dioxide. So people are saying, we've got problems, we've got a big problem occurring in our atmosphere with 100 carbon dioxide going up. I'm sorry, just 2%. 2% is nothing. It goes up 5, 10, up and down 5 or 10, 15% each day. So increases in water vapour occur in minutes too, not hours, not days. Now, I'm going to use this illustration because it was said that 100 years ago the mean temperature of the Earth was 14 degrees. So we're going to keep temperature constant, and we're going to take 60% relative humidity. We're going to look up the LenTech calculator and get that value. Then we'll go to 14 degrees still, 2% increase, we'll get that value. And while we're at it, we'll go to 65% and we'll get this value. Okay, so let's have a quick look at this. 60, 62, 65. A 2% rise, follow the blue arrow, 60 to 62 is 132 parts per million. That's 1.2 times the total 100-year increase in carbon dioxide. Now we'll take a 3% and we'll look at, follow that blue arrow, at 62 to 65, there's a 3% increase, it's 204 parts per million. It's like 1.8 times the carbon dioxide increase. Now we know we get at least 3% up and down each day, and then if we go to 5%, now this time look at the yellow arrow, 14 at 60% humidity to 14 at 65% humidity. This works out at 3 times the carbon dioxide, 100-year increase in carbon dioxide. So it's so important to see that no temperature, and we don't have no temperature conditions, we have temperature and relative humidity conditions, and we're already swamp it with no temperature together. So it's very important to see that it dominates, water dominates. That's why the water cycle is so powerful. Now let's just summarize this in one quick overview. This is the sheer power of water vapor. An increases in water vapor can double all the 100-year carbon dioxide increase simply by going from, say, by half a degree, from 18 to 18.5 as another example, or a 3% increase going at 18 degrees will cause double the carbon dioxide increase in 100 years. Now, those data are available on the web, the Lentec calculator, and they're mathematical, it's history, it's been known for 100 years, and it's accurate, very accurate. So I want to just highlight again that the natural water cycle is self-compensating, self-regulating, self-correcting and self-buffering. And that's why it's vital in this whole question of weather. Now water is very important, I know, but there's still more. The Earth is rotating. It's on a tilted axis. You and I are sitting, as we're sitting now, are moving at 460 meters a second as the Earth rotates. But the Earth is also revolving around the Sun, and it's on elliptical orbit. So we've got, on elliptical orbit, we've got change of seasons, summer, winter, and so on. We've also got clouds in the sky, which some of the radiation can't get through very well, or is scattered, or is reflected back. And then we've got things like typhoons, we've got tornadoes, we've got storms of all types, and we've got hurricanes. And we've even got blizzards. That's a blizzard there, a bit hard to see, but that is a blizzard. Massive mixing movements of water droplets, in this case perhaps snow and perhaps a little bit of ice crystals as well. And we haven't talked about lightning, and that's an effect as well. That's another effect we should. And then of course the interaction effect between waves and the atmosphere. So we've got a lot of things happening. And if you just do a quick optic over this page, you'll see the different types of storms. Some are swirling, some are directional. Lightning occurs in some and not in the others. Sometimes there's fork lightning, as you can see, and in the bottom lower one you'll see the sheet lightning, one big patch of lightning behind the cloud. And so these storms are massive mixing of water droplets of varying sizes, and it's not just solar. And so we've also got dust storms. This is a town, an actual dust storm in Australia. We've also got the sun. It's changing, it's got sunspots. And every 11 or so years, it's cyclical. And it goes through a pattern. And in some months, we've had 3 months with no sunspots at all. Now that changes the solar wind. That is the particles travelling from the sun and the quality, or I won't go into details of that, but from this radiation from the sun. And so we've got also solar flares. Now those solar flares are over 700,000 kilometres high. So they're massive bursts on the sun. And this is very important. This one here is the jet streams. Now, if you take the jet stream as it's shown now, which is in California, it's taken the hot, moist air from California up over Europe. And Europe got a heat wave this year. Why? It wasn't due to climate change. It was just the cyclical or cycle nature of the jet stream. And you can see on the left there's more than just one jet stream, and they're not in together at the same peak height at the same time. And you may recall 2 winters ago in Texas, the cold air from west of Canada came down and dumped snow all over Texas, and all the solar units went down, all the wind farms went down because iced up and they couldn't rotate because the shape of the blades would change with the ice particles condensing on it. And so Texas got a wipeout, total wipeout of energy. So we've got these massive air currents as well, not just way up but down low. And we've also got the massive ocean currents, which we will talk about. But there's still more. We've got to consider geography. For example, Denver, if you measure, excuse me again, if you measure Denver, it's a mile up. So unless the data at Denver is now normalized back to sea level, you can't compare Denver data with anywhere else. So we've got mountains and valleys and plains, the coastal inland, we've got the tilt of the earth, we've got those things happening, we've got the moon's orbit. By the way, if the moon wasn't there, the earth would wobble. As it is, the Tropic of Cancer, have moved about 200 metres in 50 years. Then we've got the Earth's precession over a long period around the sun. We've got the Earth's elliptical orbit, the Earth's magnetic field variations. We've got tectonic plates are moving and underwater active volcanoes. We've got hydrothermal vents, and at the south of America we see some of the floating ice just above the Arctic Circle, Antarctic Circle, is actually melting. It's melting from underneath. It's not climate change at all. It's simply a vent. And some of these vents, by the way, are carbon dioxide, and total carbon dioxide, and methane. Some are total methane, and some are liquid at very high pressures and under depths. We've got ice melting sheets as well, and they're melting from underneath, as we said. Now, over and above all of this, we've got a hot equator and cold poles, so the energy is travelling from the centre up and down as well. So we're getting circular patterns as well as rotating type patterns. And so what are we doing? All we're doing is worried about radiation and fossil fuels, and maybe we should be looking far further than that, and not worried about the effect of animals and a few animals causing an increase in methane. Well, let's go on with precipitation on Earth. As I said, there's 13 million tonnes a second, 423 trillion tonnes a year, 13 million tonnes a second. They're cloud microdroplets. They amalgamate or agglomerate to form liquid droplets. So the little fellas you can't see, they agglomerate and form a big droplet. They can't stay up there, so they rain. Now, cloud droplets go to rain droplets. And this is quite interesting if you're interested in numbers. 3,000 trillion per second glue together. Amalgamate, agglomerate together. 3,000 trillion is 3,000 million per second get together to form a raindrop. Now, it's even more dramatic. I've examined the surface area of droplets and so on, and the surface area change per hour is 42 times the surface area of the Earth per hour. 42 times the surface area per hour, and it's massive, massive. Now, coming back to carbon dioxide, because everyone's focus on carbon dioxide is increasing, and this is a graph of carbon dioxide going up with time. It's not monotonically or uniformly going up. It looks like it, but there's a lot happening. It oscillates six monthly, and it's not random. It's a clear cyclical oscillation, as you can see. Now, if we take that same type of graph, it's basically the same data, but I've put something on top. If we look temperature there, you can see that temperature does not, it goes up and down, it changes with time, but it's not going up cyclically every 6 months. And so you can't connect temperature with carbon dioxide. End of story. And it's on the web. And so we need to look at the NOAA, as you can see the reference in the corner there. It's just to highlight that. And so that is important to see that that is occurring. 10 parts per million in 6 months and down about 8 to get a net of 2 approximately. Now, it's important and honest to say that the 99% oxygen, nitrogen and argon get involved, and they get involved by collision. So now we've got kinetic energy. All we're talking about is thermal energy today. We must talk about kinetic energy. Kinetic energy is motion. It's collisions. Rain is colliding. Droplets are colliding. Molecules are colliding. And so energy is colliding. It's not just, energy is transferred by motion, by impact. And so they get involved. Our big problem today, of course, is global dimming. We'll talk about that in a moment. And we know that most of the volcanoes cause it. We know burning off trash and rubbish cause it. Incomplete combustion is the problem. But we've got burn-offs, and we know we've got smoke, which has got particles in it, and so on. And most of the active volcanoes are under the sea anyway. But the question is really, so what? What is major? Well, water droplets. Water droplets are major. 24 times higher in concentration than CO2, 500 times higher than man-made CO2, and 5,300 times higher than methane, and 33,000 times higher than nitrous oxide. So it's a pretty massive change. So that's just the amount, that's just the quantity, that's just the concentration. Now, if you look at the effectiveness, and this is based on the envelopes of the radiation curve that's in the literature, we'll see the radiation effectiveness, allowing for competition. We'll see that carbon dioxide is 35 times greater in radiation effectiveness than carbon dioxide, 5,900 times greater in radiation effectiveness in methane, and 1,400 times greater in radiation effectiveness than nitrous oxide. So we can see that why the water cycle, why the water in the atmosphere, and of course we know that carbon dioxide doesn't exist as a constant concentration. It's been gobbled up all the time and used, and of course we get the oxygen from it, from the leaves as well, from there. It's interesting, just to finish off on that slide, is that water vapor is 700 times more radiation effective than man-made carbon dioxide, man-made part. Okay, so we just said 35 times more effective than carbon dioxide and 700 times more effective than the man-made. And that's what the emphasis is on, man-made. So what are the real concerns? Well, it's not just radiation, and it's not just fossil fuels, it's not just industry or vehicles, and it's not farming methane or nitrous oxide only. No, the big problem we have is incomplete combustion. The amount of dust, dirt, rubbish in the air, and also the atmospheric pollution, which of course are chemicals, biochemicals and stuff, are in the atmosphere, which are affecting our radiation in, radiation out, as well as our condition. And of course, the rain scrubs the atmosphere of this stuff, and some carbon dioxide, by the way. So don't forget, we've got breezes, we've got thermals, we've got wind, we've got clouds, we've got storms, hurricanes, cyclones, tornadoes, typhoons, jet streams, trade winds, roaring 40s, just in the air. And on the tides, we've got conveyor belts in the sea, we've got upwellings of water travelling up to the surface, we've got waves, thermal storage, El Niños connecting the two, and then we've got other things which we've mentioned of just a few of them today. Tectonic plate, fissures and cracks causing underground volcanoes, and also hot liquid to come up, or gas and so on. We've got sunspots, solar wind. We haven't had a chance to talk about any of this, and the cyclical nature of the Milankovitch cycles, which are periodic. These things, there's a whole raft of them that we haven't talked about, cyclical behaviour. Okay, water vapour. It's the only gas that changes phase, and that is the bigger picture, and that's the heart of weather change. Thanks very much. You can contact me if you like. There's my email, geoff.duffy@likecost.com, and I will try and answer your questions. I've got several little handout sheets on topics, and if you're questioned or concerned about the issues, because I've highlighted that I've used only the material from the web. So thanks very much.